Back in the 19th century, there was a statistician in Britain by the name of George Yule, and he famously said that in our lust for measurement, we often measure that which we can rather than what we wish to measure and forget that there is a difference. And so this is a challenge that all of our remarkable panelists today will be tackling because they are sort of at the forefront of figuring out the next generation of biomarkers. So welcome Max, Kari, and Stephen. But before we get into all of this, I wanted to spend just a quick minute with all of us reflecting both on the utter beauty but also the unfathomable complexity of the human body that all three of our panelists are dealing with. So if you would, please humor me for just a minute. I'd love for you to bring your attention to your body. And I want you to see if you can imagine the 30 trillion cells with 14 quadrillion mitochondria who are also connected to the 30 trillion bacteria, viruses, and fungi that make up your microbiome. And all of these cells, even in this minute, they are listening to the rhythm of your life. So how you eat, how you move, how you sleep, how you manage your stress, who you connected with last night at the party, how much time you spend in nature, as well as all the chemicals that you are exposed to, including the 8.3 billion metric tons of plastic that you and I have consumed that's in our landfills, but also seeping into the air that we breathe, the water that we drink, and the soil that our food is grown in. And all of this constitutes our exposome, right? All of our exposures from the moment of conception till the day that we die. And as our cells try to make sense of this exposome in order to keep us healthy, they engage more than 19,000 of your genes that express more than 30,000 proteins that make everything possible, right? So your growth, your repair, the cell communication, the more than 1 billion metabolic reactions that happen every single second in your body. And then all of this blood goes through your lungs in about every minute. And when you breathe right now, for example, we breathe 22,000 breaths in a day, and we exhale 11,000 liters of air that contains not just carbon dioxide, but up to 1,000 organic volatile compounds. So our body is truly a wonderland. And health is not something static. It's this dynamic conversation between our inner and outer ecologies. So as we dive into this panel today, what our brilliant experts are going to shine a light on is how do we make sense of this complexity? How do we come up with biomarkers that are not just sensitive, but also accurate, that are dynamic, that are cost-effective, so that clinicians and researchers have a more nuanced view of health? So the way this is going to work is we are going to do a lightning round of talks. And then we're going to talk to each other for just a little bit. But then we mostly want to hear from you. So please keep your questions and your comments ready to go so that we can end on time. So first up, it's my great pleasure to introduce Dr. Max Allsworth. He is the Chief Science Officer at Owlstone Medical. And he's going to take us on a journey of our breath's volatile signatures. Max, please.
So what I'm going to talk today about is breath analysis and how it can be used and how it can be used in the home by everyone. The first thing is about what are breath volatiles. Why have you got so many chemicals on your breath? They represent pretty much everything you're exposed to in your lives. They're the food you eat, the things you drink, the chemicals in the environment, but they're also representative of what your body's doing. They're endogenous compounds that are generated as you process sugars, as your muscles operate. These mixtures of chemicals represent that everything's happening in your body and the exposure and the risks that you're involved with. One thing Owlstone has been doing is building up an atlas of all these chemicals. With the support of one of our investors, the Gates Foundation, we sort of built an interactive sample biobank that links all those different chemicals in breath to the patient data that's there, where we can apply models to understand what's happening. So there's all these compounds on breath. But what can you do with them? And I'm going to do quickly 3 examples of tests under development at the moment. Some already available. This one's the device is FDA approved. Others in late-stage clinical trials. So this first one is talking about hydrogen and methane on breath. Now, this comes from your microbiome. When you eat any carbohydrates, they need to be broken down by the bacteria in your gut. Now, if some of those bacteria aren't in the right place, or there are too many of certain types of bacteria, that fermentation produces gases, hydrogen and methane. They drive some of the discomfort, bloating, and all the side effects of IBS. So being able to measure those all the time gives you great capabilities in diagnosing problems. And this device is a pure point-of-care device, something you can take home with you, links to your phone. The app that it's connected to tracks symptoms, your food, and the hydrogen and methane, and provides the information to a doctor to be able to make clinical decisions. And quick example of that, this is a case report of something you could never do with with standard testing at the moment, because you wouldn't have the number of data points. So each one of these blue dots is a measurement of methane, one of the 2 gases this device is measuring. So every day they were taking multiple measurements of their methane as they ate different foods. And these methane levels for this patient was particularly high. It was causing all sorts of GI symptoms. The doctor was consulted. They identified methogenic overgrowth, so too much of a certain type of bacteria, and they were given an antibiotics regime. That was the standard of care. But as you can see, after that first antibiotic dose, it knocked it down a bit, but it didn't solve the problem. And normally in the standard of care, they would have gone on to something else. But the doctor could quickly look and see it did do something. It was just, it wasn't a harsh enough treatment. So a second treatment knocked it down. And this is where this sort of continuous information, the amount of data you can get from a breath sample, which is available all the time, you can always breathe, or you've got other problems. So lets a patient take many, many samples and really delve deeply into the data that can be generated. But that's not the only applications we've been exploring. Another big problem in the world is liver disease, especially advanced liver disease, and the kicking into cirrhosis and decompensated cirrhosis. And the problem is definitely real because it's most often diagnosed in emergency rooms. So 50% up to 75% of people find out their liver's decompensated and it's too late to do anything about it in an emergency room. So there's definitely something we're not doing right today. And here we were looking and thinking, how can we use a breath test to help this? And actually, you test your liver every day when you eat food, drink, particularly alcohol. Your liver's there to take the chemicals out of your bloodstream, metabolize them away so they're safe. So every time you eat, you are challenging your liver. If your liver's not working very well and you drink a glass of orange juice, instead of those compounds in there being sucked out of the bloodstream and processed away, they go straight into your circulatory system and are there being continuously breathed out. So you can make a test with orange juice and a breath test. We went slightly more controlled than how much pulp is in orange juice to how much compound you receive, and build a small test where you receive a cocktail of compounds, those 3 compounds that you drink. A few minutes later, you take a breath test. What this is doing is looking at how those compounds were extracted from the liver and how they were metabolized. So a simple core functional test of the liver. Now, you might think there are really simple liver function tests out there already. There are things that are called liver function blood tests, but in effect, those really look at how much damage, they're damage markers in the liver. They're not telling you how much function the liver has. And there's imaging techniques, as you'll see, ultrasound and things to measure the fibrotic state of the liver. But again, they're looking at the damage, not how well your liver is working. So having these sort of tools that let you really screen at what the liver's functionally doing lets you test orthogonally what's happening to the liver, But also, these tests are, like, you can post them out to someone. They bring screening to everyone. You can try and reach those patients that otherwise wouldn't be found till they hit the emergency room. And if you get them early, you don't have, the treatment can be lifestyle, and there are a couple of drugs now. It's much simpler treatment. If they're caught late, treatment is very difficult. So the final one is lung cancer, the biggest cancer killer in the US. And this is what Owlstone was founded on, Owlstone Medical was founded on. It was trying to find a way to get lung cancer tests to the individual in the home. There are tests out there at the moment. They have limitations. They either can't detect cancers at the earliest stage when treatment is most effective, or they require hospital visits, people are resistant to it, and their compliance is really poor. Like low-dose CT is no copay, sort of free in the US, only 4% people comply with it, and state to state, that's in some states it's incredibly low. So people just don't want to do the test. So if we can bring a test to a patient, we can hopefully increase that compliance rate as long as we can get the good enough sensitivity at early stage. And I talked about using a probe, taking something and testing your liver. We've taken exactly the same approach with lung cancer. So here we've looked at an inhaled probe, an inhaled compound that you breathe in, and then this reacts with certain enzymes in the tumor microenvironment, and you breathe it out again. So this is a test that, again, can be done at home. There is no limitations on who can do it, as long as you can sort of easily suck in a dry powder from an inhaler, like many children do for asthma. Wait a few minutes and breathe out into a collector. This gives you a at-home, hopefully highly compliant test. And we started this test without using an inhaled form. We injected the probe into patients. We performed a stage 2 trial last year, and even at the earliest stage 1 cancers, we were already getting close to 68.5% sensitivity. So you can detect cancers this early using these sort of approaches, and we're aiming to, we're running a stage 1 this week on our inhaled probe, where we hope to make this test usable for everyone. Okay, and I'll just close up saying I've given a whistle-stop tour here, just described the different applications you can use for breath. You can see there's a thread through them. It's about getting these diagnostic tests into the home, maximizing compliance, finding diseases as early as possible, where they're easily treatable. And I think it fits with what other speakers have been talking about, prevention. These are all hitting the diseases when they're asymptomatic, early enough that you can make a difference, like maximizing health for as long as possible for everyone. Thank you very much.
Fantastic. Thank you so much, Dr. Allsworth. Next up, we have Dr. Kari Nadeau, who is going to talk to us about the ramifications of the plastic both outside and inside us. She is a John Brock Professor of Climate and Population Studies and the Chair of Environmental Health at Harvard Chan School of Public Health. Kari, please take it away.
Thank you. It's great to be here. I'm excited to talk to you about something that's on many people's minds today. But importantly, it's also in your mind, and I'll talk about that. So we are in an era called the Pleistocene era. This is taken from Texas, where one of their floods deposited a lot of plastic in one particular layer. This is not just in Texas. This is in many parts of the US as well as the world. That plastic will probably last for thousands of years. And you see this embedded in the earth. Unfortunately, plastics are also embedded in our body. And with that in mind, how do they get into our body? Well, microplastics versus nanoplastics are important because size matters. So anything less than about 1 millimeter is called a microplastic. Anything that's less than about a micrometer is called a nanoplastic. Why is that important to you? Because these can be absorbed through the skin, they can be absorbed through the gut, they can be inhaled as well, and that's a problem in terms of overload of plastics in our bodies. This is just what we breathe in, for example. How many of you heard that you eat about a credit card's worth of plastic a week? In Indonesia, it's about a day. But that's just eating. That's just through our gut. This is inhaling. and I'll talk about this as well. But we have about over a year the height of 2 giraffes, over a lifetime potentially the height of the Eiffel Tower, and in places like Indonesia, the height of a mountain. So when we think about what we're doing and how we're getting exposed to microplastics and nanoplastics, it's through bottled water, water that's in bottles that are plastic. It's through beer. It's through air. You notice I didn't put wine on this list. We don't know that data yet. Tap water, seafood, sugar, salt, and honey. Importantly is that per year, the average person is consuming between 78,000 to over 200,000 particles of plastic. And why is that important? We know a lot about how in marine life, how they break down these plastics. And there's about 14,000 different chemicals in a typical plastic mixture. And of that 14,000 chemicals, about 4,000 are known to be toxins. Toxins to the planet, toxins to marine life, toxic to humans. And what happens is they break down, and they break down into these components. Phthalates and BPA, you've all heard those things we worry about in terms of being estrogen mimetics and causing hormonal problems. You've heard of polycyclic aromatic hydrocarbons and styrenes. They can be associated with cancer. And importantly, you see nickel and lead on this. Those are 2 heavy metals that can also be associated with inflammation and increased health disease. And so why do we worry about plastics? Well, unfortunately, they exist from head to toe in our bodies now. Thanks to a lot of studies that have occurred throughout medicine, we're seeing that microplastics are not only in our brain or our hearts, but they're also in umbilical cord blood. They're also in placenta, they're in semen, they're in ova, they're in follicular fluid. And these are associated with diseases. Many papers have been published now over the past 5 years showing the association of microplastics and disease. Like John had mentioned, the CNN that we worry about, cardiovascular disease, neoplasia, and neurodevelopment disorders are all unfortunately associated with microplastic burden now in our body. For example, a recent paper in Nature Medicine came out this past year showing that the number of microplastics in someone's brain is associated with dementia. There's also data now that came out of the New England Journal of Medicine showing that if people have high amounts of microplastics in their carotid arteries compared to those that do not, you have a 2-fold increase in your rate of stroke and heart attacks. That's similar to smoking about 7 cigarettes a day for a lifetime. So microplastics are a problem, and we need to think about how we can work to manage this. This is a video that was done through AI by my colleague in Australia, Peter Smith. And this shows you in the typical adult brain, there's about a teaspoon's worth of plastic. Now, it's not this size, but this is, for an image sake, important to show that this plastic is added to the load of plastic that's also in our bodies, throughout our bodies, not just in our minds. So with that in mind, how are we going to measure this? We're using at Harvard in my laboratory a laser-directed infrared system to be able to measure microplastics. And the reason this is important is because we can take 2 drops of blood, and this is, for example, a microscope in 10x, and that shows you the plastics that were in a typical healthy person's blood at about 10x. And what we can do with this LDIR machine is look at the different types of plastics in that person's blood. Why is this important? Because you can go back and look at the fingerprint, I'm going to call it, of someone's plastics and what they were exposed to. For example, polyethylene is from soft plastic, and it's also from microabrasion and scrubs that people use for their face. So we were able to tell this person to use less of that. We're also able to say that the number of rubber particles that was equivalent to silicone was associated with the cooking equipment that they were using in the kitchen. And we were able to, over a period of 3 months, show that this plastic was reduced in their plasma by 80%. So the reason why I want to mention this is because we can measure, we can monitor, and then we can manage. And about every 3 months, we can look at someone's plasma and see how well they're doing to reduce plastic use. Importantly, we can also talk to policymakers. There's bills in California right now to reduce plastic use across our state, talk to businesses, and look at safer alternative products. So one can use home filters, for example, to reduce your tap water exposure to plastics. There are ceramic filters as well as life straws that you can use to reduce plastics in the water supply. But importantly, there's plastic alternatives now being used, not just in regular household products, but also in the medical field, especially in hospitals. So I just want to talk about the fact that these are new businesses that are coming out, biomatter, organisms and tissues, as well as monomers and polymers that could potentially be used as alternatives and hopefully be much healthier. So in conclusion, human exposure to micro and nanoplastics is increasing. These are found in most organs of the human body. It's associated with pathology and disease. These, unfortunately, are harbingers for microorganisms, and so this is also another place where antibiotic resistance will increase with the load of microplastics in the human body. Methods for detection and characterization need further standardization. We're doing that under research now in my laboratory at Harvard, and the environmental policies are urgently needed to reduce plastic exposure. So in my lab called the Allergy, Extreme Weather, and Exposomics Lab, we're doing research not just on microplastics, but I have some of the kits that are in the living lab to show you. We can take 2 drops of blood and not only look at microplastics, but also other toxins in the body. And this concept of exposomics is very important because it's what you're exposed to, both good and bad, at any one point in time and over someone's lifetime. So now we can actually look at what you might have been exposed to when you were 2 years old based on what lies in your DNA. So this is a very important concept. We're doing more and more in terms of research on this, and there needs to be more research, not just in my own lab, but around the world to be able to understand exposomics and how it can improve the health span. Thank you.
Thank you. Thank you, Kari. Last but not least, we have Dr. Stephen Williams, who is the Chief Medical Officer at SomaLogic. He's going to talk to us about Upload's Proteomics Symphony.
Thank you. Good to be here. We are all in the information business. We care about ourselves living longer and our patients living longer, so we want to predict future risks. We want to work out, can we predict what interventions would be good for someone? We want to be able to detect whether an intervention actually worked. And we want to be able to discriminate between snake oil and things that really work. So we're all in the information business. The question is, where is it? Where does this miracle of information about the whole person and about all these different systems reside? The bet that we've taken is that it's in proteins. If you measure enough proteins, you can get a map like this. There are 7,000 spots on this map, each one of which is a protein, and it's an information landscape, so the spots are distributed mathematically over the picture here. Ones that are more alike are close together, and ones that are less alike are further apart, and they're color-coded. On the left, you can see those blue spots are the ones that are predominantly influenced by genetics. So you can see that Francis Collins was half right when he said that genetics is going to explain everything about every disease known to humans. But only half, because the other half of the proteins are mostly influenced by something else, the environment. But the nice thing is that proteins catch both of those kinds of information, the environment and genetics. And we're going to start looking at what use that might be. So this is a volcano plot. You may not be familiar with volcano plots, but like real volcanoes, the bits you care about are the bits of lava that fly the highest and move the furthest. And those are the protein spots at the top of these graphs. The key point here is if you don't measure it, you can't find it. And not all of these proteins are things that you would predict from what we already know from human physiology. So again, what our thesis is, if you measure enough proteins, you can find effects that are completely unexpected and new. And they don't work on their own. Yes, of course, in medicine we do use individual proteins. But proteins have evolved in networks to transmit information, in patterns. So if you measure thousands of proteins, you can find the patterns. This is my "we are not Theranos" slide. But the serious point here is you can develop a technology that's precise and sensitive and useful. But if nobody trusts it, then it won't get used and it won't be useful. So we have a lot of publications, many of which have got hundreds of citations. But now we move on to, what is the point of all of this? What we've done over the past decade or so is to measure thousands of proteins in about 250,000 people with about 1 million participant years worth of follow-up data. And what we've done with that is to try and find the protein network patterns that relate to outcomes and that relate to current health state, and the ones that change when you intervene in a good way, and the ones that change when you intervene in a way that might be harmful. So today we've developed this group of SomaSignal tests, each of which is a mathematical model, a subset of proteins within the assay itself. The assay has two versions today. One measures 7,000 proteins at once. The other measures 11,000 proteins at once. These models between them today, they only use about 600 proteins with very little overlap, and I'll talk a bit more about that. In the future, we hope that people like yourselves will become equivalent to genetic counselors, but be proteomic counselors, because even though the SomaSignal tests are useful, they don't cover every impact of every intervention and every lifestyle change. And we think that as we learn more about human physiology, we'll actually be able to interpret individual proteins as well. But that's for the future. So these are the tests that have been validated so far and in those publications that we talked about. And when we saw earlier about the whole person, it's not simply a urologist or a single system. What we're saying here is that you can measure any one of these or all of them from the same blood test at the same time, and you can measure changes over time. So you can see they do cover cardiometabolic health. That was our focus, and cancer. We may have a chance to talk about that later. But the likelihood of developing cancer is very dependent on environmental exposure and immune surveillance. And we think proteins are really good at following those things, but those tests are in the process of being validated. So how does this work in practice? How does this help you work out whether a particular change in lifestyle or pharmacology actually did something useful? Well, this is the results of a test of a dietary intervention. It was a pretty severe caloric restriction study. Each of the rows is a proteomic test. And each of the spots is, well, what happened to that test during the year in this study? And you can see that dietary intervention in people who lost more than 10 kilos, the purple spots, it improved a lot of body composition. The glucose tolerance test is the proteins mimic the result of a glucose tolerance test without fasting and without glucose. And you can see that there was a huge improvement in those tests, as well as cardiovascular events and body composition, as you might have expected. Some of these changes weren't slow. Even though that was a year study, as a component of one of the studies there was that you could measure these things over time and you can see changes quickly. The tests have also been used by pharma. We've heard some information this morning about GLP-1s, and Novo has published on using the SomaScan assay. And they used it in both ways that I talked about at the beginning. They measured the changes in individual proteins, and you see one of those volcano plots where they found 495 proteins that change. Many of those in pathways that impact some of the benefits and some of the disbenefits like muscle mass loss. But on the right, they also measured the cardiovascular event prediction test. Now, you might say, why on earth do you care? Because they did this big outcome study and the event rate was less. So why do they need to show the protein effect? Well, the key point here is that their cardiovascular event study was 57,000 participant years worth of data. It took them 7 years to run. The benefits, those cardiovascular benefits to those patients were all delayed while they ran a 7-year study. We're interested in measuring those things today in individuals, and that's what they did on the right. The bars crossing the dashed line of zero change are the placebo groups, and the ones that fell below that are the proteomic predictor of cardiovascular event rates falling over time in much smaller studies. And talking of much smaller studies, this is a randomized controlled study of providing this information. So this was run by Rosalind Gill, who's sitting there at the back. People told us that behavioral change, now maybe I don't think this audience believes it, but behavioral change is a lost cause. That even if you provided people with an individualized, accurate assessment of their likelihood of dying, developing heart failure, or having a stroke, they wouldn't change anything. So what we did was to take a group of 400 people and we randomly assigned them to be informed or not informed. And we measured prescribing rates of enhanced cardioprotective drugs. That's the plot on the left. The blue section is the people who were informed, and these were all people who should have been on an SGLT2 inhibitor or GLP-1 or more intensive statins, but weren't. And you can see the prescribing rates went up to between 30 and 40%. On the grey side, you can see that the uninformed group, there was a clinical trial effect from extra attention, but they only went up to about 10%. So providing people with individualized information changes behavior. And if you want to visit the Learning Lab, you can see whether it changes your behavior, because you can get this done yourselves. Thanks.
Thanks very much. So what we're going to do now is please get ready with your comments and your questions. We'll take them in a little bit. But before that, I just want to make some observations with the group here and kind of see what came up for you as you were listening to each other in terms of both some of the challenges that you might be noticing that are similar across the board, but maybe also some opportunities for collaboration, especially when you think about exposomics and where that needs to go. So maybe, Kari, I can direct this to you, is, one of the themes of this summit today is women's health. And the thing that I discovered, when Jordan and I wrote a white paper that we collaborated with your team on, by the way, ask us for it, we'll point you to it. One of the things I was really surprised by was that when we get exposed to microplastics, it's not just a microplastic particle, you get 3 for 1. You get the plastic-associated chemical, like the phthalates and the PFAS and so on, and then the environmental toxins. And there's very strong evidence for them being endocrine disrupting chemicals. So could you speak to that a little bit in terms of women's health?
Yeah, I think this is really important as we think about all of the opportunities that we're talking about at this gathering. There's a lot of great things that we've discovered over the many years in terms of including our health span and increasing years since the early 1900s. But one thing that we have not done well is to assess the state of microplastics and nanoplastics and how that's affecting the human body. And I think the breakdown into hormone mimetics, like the phthalates, and how that might affect women's health is critical. We're doing a study now as how it's affecting infertility, because infertility is increasing in our country as well as throughout the world. Not just for microplastics, but microplastics are also associated with pollution now. So I think when we think about connecting to Owlstone, connecting to SomaLogic, what would be great to see is breath tests that we could perhaps be able to infer issues with estrogenic changes, with hormonal changes, men and women, because this is affecting both. And then in addition, for SomaLogic to be able to perhaps link together and collaborate with looking at a proteome profile that could be associated with microplastic burden, and looking at to what extent that proteomic profile might be associated with inflammatory disease, hormonal diseases, and then also cancer. So I think these are the things that we can look at, putting an ensemble of data sources together with machine learning algorithms to really think about a composite endpoint that one could then detect disease and also management of that disease with these, with these tools.
Yeah, wonderful. Max, any thoughts on that? And did you have a question for Stephen and
Yeah, so the interaction between small chemicals and plastics is very significant as well. Like this, chemicals permeate into microplastics and live in there, so they act as a source inside the body of those chemicals would otherwise be cleared very quickly. They end up being, they ended up stuck in those microplastics. So that then you get the combined effect of prolonged exposure to chemicals you wouldn't normally be exposed to, as well as the direct effect of the microplastic. And those are the sort of things we do a lot of work measuring. And so I can definitely see a correlation there and a way we could explore. On the question side, or the challenge with microplastics always seems it's how do you do anything about it? And I did wonder if there was like one thing you could change, you had a magic wand or a presidential order or something that you could just say, do this, get rid of this. Like, where do you think the biggest source is? Because I assume a lot of it's at work and in business rather than just in your home that you can fix these problems.
For that we know right now, the biggest bang for your buck, as it were, the biggest bang for your change would probably be in soft plastics. Avoid them. Do not microwave anything that's plastic. Do not use plastic bottles any longer, and try to avoid saran wrap. Those are the most associated with polyethylene, and polyethylene up to now has been the most highly associated chemical from plastics associated with neurodegenerative disease as well as cardiovascular disease. So I hope that's an answer that is helpful. We can manage that, we can change that in our living styles. Not everyone can, but that's just the tip of the iceberg. We're learning, so there might be some, if you ask me next year, it might be different.
And soft plastics are the ones that would absorb the most chemical as well. That acts as the biggest source for exposure to the rest of the body. And Stephen, I was super interested in your talk, actually. But how, on the sort of tying together with the plastic side, how, so I'll ask this carefully, the changes that you get, how do you pick out those differences from normal phenotype changes over someone's lifetime? I think about that because back in the day when I still worked in the lab, I had to monitor a certain enzyme level because I was working with something quite toxic. Mine stayed stable. The colleague I was working with, they had a big jump in a certain enzyme in their body, so that they had a lifestyle phenotype change. That must be happening quite extensively in the data you're showing. So how have you pulled that out? And how would you separate that from exposure-related things, a change that's happened, been driven by what you've been exposed to?
So clearly, I mean, there are proteins that relate beautifully to aging. You can make a lovely age clock model that predicts your chronologic age and follows and uses proteins that just track with age. But when we're trying to predict health outcomes, we let machine learning choose the subset of proteins that most closely relate to that phenotype or that risk. And if you include, in the training population, if you include all of the confounding variables, people of different ages, on different drugs, different sexes, and different ethnic groups, then you enable the machine learning to pull out the proteins that survive those confounding variables, and potentially to include correction proteins for other things like age. So often, for example, FSH or PSA will get included in models that are nothing to do with those hormones, but the machine learning is using them to correct for female, older women or older men, and it can incorporate them in the model. So I think that it's kind of the opposite of a clean physiology experiment is a beautifully matched set of cases and controlled with no other variables. A beautiful machine learning experiment is a really dirty experiment where you enable it to find the robust ones and correct.
Were there any questions from the audience? Any comments, questions? You can raise your hand. Or go to the mic. Yes, please.
Thank you. It's Gabriela Vilero from Camino Partners. The science is undeniable, and the question that comes up for me is, what are your observations in terms of the individual's willingness to pay for this knowledge, for this journey? Like an example on the OMED health side, low FODMAP has existed for many, many years. How does the cost of a device would compare for just trial and error in low FODMAP and so forth? And similarly on the blood testing side, it's undeniable, like observing like how much you can get with just a simple small blood drawn. But at the same time, as we try to bring health to a broader set of audience, what are the green shoots that you're observing in terms of people's willingness to learn and to then take the step and participate in what you're doing?
Thank you.
Yeah, I can start with that. On the IBS applications, I think the patients are often very driven to solve the problem. The number of days of work missed due to digestive disease problems is huge in the States. There is a driver for paying for those tests, and you can get reimbursement as well. So there is a route there. I think it's much harder in liver disease. As I said, it's silent, asymptomatic, and no one worries about the liver until it's a problem. So getting that paid for is much more difficult, and that does push a need for a very low price point. And even then, it's like getting people to take the test is difficult. I don't know if anyone else wants to drive it.
Well, I like the question, but what it really is a manifestation of market failure, and that when you look at, we want to measure things which are pre-symptomatic, pre-disease. They're viewed as not medically necessary by insurance companies or by Medicaid and Medicare. Screening tests require an act of Congress to approve. So what we're saying is that in the face of a complete market failure in terms of traditional diagnostics, now we're in the cash pay business, and I think that it's a perception of value for money. For us, it's if you added up ways of getting all of that same information from treadmills or glucose tolerance or coronary, you add it all up, and it's thousands of dollars, and we're less, and it's easier. So I think the value proposition can be there, and the challenge to us is to keep on lowering the costs and making it more and more accessible. But the fundamental problem is there's a failure of the traditional market for diagnostics for things which are pre-symptomatic, early warning, not medically necessary.
Thank you. Thank you for that question. Mark?
I have a question with regards to the microplastics. And I think, so many of us in the health space, I'm a physician, we see consumer-based medicine where patients are coming forward and asking for vitamin IVs and all sorts of other things. And we think, gosh, if it does no harm, why not? But is there an inherent harm in vitamin IVs and doing IVs if maybe the risk maybe outweighs the benefit? And what's being explored in terms of alternative mechanisms for non-plastic tubing and other things in the healthcare industry, because we want to do no harm.
Absolutely. Let's follow Hippocrates as much as possible. I think to that end, the national healthcare system in the UK is going as ecologically friendly as possible in their healthcare supply chain. And so that's about 30,000 companies that not only have to agree to net zero in terms of renewable energy sources for the National Health Services, but it also means ecologically friendly plastic alternatives. Now, I say that it'll be very difficult to become pre-1940s and be completely a plastic-free society. And medical care is one in which plastics have potentially improved some outcomes. But when you look at IV tubing, when you look at some of the bags that we use and some of the plastics that we use and some of the wrapping that we use, we are potentially doing harm. So with that in mind, there are alternatives. Baxter, for example, is making a fiber type IV tubing that is just as flexible. I showed some of the other alternatives on my slide. So I think as we get smarter about plastic alternatives, we get smarter about looking to nature, to what alternatives there are for waterproof type bendable equipment that can be used in the healthcare system. I think we are going to get there. It's going to take resources, it's going to be expensive. But I think what I see, to answer the previous person's question, is there's a drive, there's a personal drive on behalf of the public to know what they're exposed to. What they don't know could hurt them. And so I think we can multiply the message that we need to do better testing, and we need to have better products, and we need to reduce plastic pollution.
Thanks very much. Nicole?
Thank you. Thank you very much for this session. I have a quick question around removal of microplastics. So there are some technologies that exist in the apheresis space that are removing the lipoproteins, obviously very medically indicated. Now, those are moving into the we will remove all your plastics from your body space. So I'd love to have your comment on the validity of these.
Absolutely. And I'm not Orlando Bloom, but apparently he was one of the first people to have one of these plasmapheresis done. We're trying to now do a research from this group because we were very interested in before and after, are you actually reducing your plastics? And so we contacted the company that Orlando Bloom used, and we have yet to hear back from them. But I would say to all of you, if you have patients, if you yourself are thinking about this, please be careful, because the very same things that are being used for apheresis or plasmapheresis actually do contain plastics. And so the filter has plastics in and of itself. And so let's do the research to be able to answer that question appropriately, but right now I don't have the full answer. And I don't know if that's the way that someone would want to approach this problem.
Yeah. Any other questions or comments? You know, one of the things, Kari, I remember when we were writing the paper was that with every liter of IV fluid, there's 58,200 microplastic particles that get injected. And it's not just that, it's also the DEHP, that is the plasticizer that's used with the PVC bags and tubing. And one of the things that, you know, what I love about all your work is that it's really highlighting the importance of tracking our environmental exposures to what's happening with the multi-omics technology that we have. And I was really sad a couple of months ago when we came very close to signing the International Plastics Treaty, but it fell through because, well, nations couldn't agree on reducing the production of plastic. So maybe in the last 3 minutes that we have here, just a final reflection from each of you on what is the one wish, if you could put out into the world in your field, what would that be? What is that one big wish that you would love to make happen? So Max?
Oh, that's, I think it would be to what Stephen mentioned, the change how diagnostics and early disease are treated, or valued for an investment purpose as well. The device I was showing, that treatment plan, our objective was to get people well so they didn't need to have the device anymore. That was the end point. It was 3 months and they're better, and they may not need the device again for years, rather than a therapeutic where they might be on something for the rest of their life. So the value doesn't really reflect the value to society of finding disease early and dealing with it when it's when you can make a difference and change their life for good. So yeah, some way to change the core economics of diagnostics and early detection.
Yeah.
That was what I changed.
Well, hopefully some of the folks in this audience can kind of support you as you do that. And congratulations, Owlstone Medical just got a $49 million award from ARPA-H.
We did. So thank you. So I talked about using probes for lung cancer detection. Mm-hmm. That technology, that's in human at the moment, but the next level back, we've been developing suites of probes that could be used for over 30 solid cancers. And we're working with MIT, Georgia Tech, and Boston University to develop and test these probes out. And that's what the ARPA-H grant that we received 2 weeks ago, just in time before the shutdown, to develop that over the next 5 years. So it's a very exciting project. And again, it's a multi-cancer screening application where everything could be done in the home. It's a complete home test.
That's such a fantastic vision to be able to do that at home. Thank you. Kari.
Thank you. You know, I think about this, and we've only been able to talk about microplastics today, but there are many other exposures that affect our bodies in a way that's deleterious and can increase our health risks. But there are also behaviors and exposures that improve our health. And so to me, to be able to understand this concept of exposomics, everything all at once at any one point in time, as well as over someone's lifetime, and to be able to get better at measuring. I've seen just in my lifetime of being a physician how much the tools here that we've had spoken about have improved our ability to predict potential diseases as well as try to prevent the onset of diseases. So I'm excited about this tool and being able to spread that knowledge to help others for the social good.
Fantastic. Thank you, Kari. Stephen?
I think I want to see the commitment to preventative health, scale beyond the committed people in this room. And that probably takes markets like the Middle East, we heard from Nicole, and maybe like Japan, where they care about long-term preventative health. They recognize that they have problems that can be tackled with some existing interventions, and where they're creating a way of actually solving the market failures. And I'm hoping that those places will show the rest of the world the health economics of preventative health can be good, and that they'll lead to a change in the commitment and the financing of preventative actions. Scale it.
Well, may that wish come true. And please join me in thanking Matt, Kari, and Stephen. Thank you. Really good to meet you.
Hi, my name is Kari Nadeau. I'm from Harvard University. I direct the Department of Environmental Health here. I also oversee a laboratory. We test for microplastics in the blood. We also test for microplastics in other things as well. Importantly, is you can be part of our citizen science study to be able to understand your microplastics in your blood and what that means, where it's coming from, and what you can do about it. And that's the most important item here, is it is actionable evidence to be able to help you change your lifestyle to improve your health. So with that in mind, we could send you one of these kits at your home. You send it back to us after you use it. It's very easy. It's just a very simple blood draw, only about 3 drops of blood. And then it's very painless. You send it back. You can do your whole home, including children and older adults. It is very helpful to be able to bring it back to us through the mail. It's totally fine to do that. My colleague, Colin Skeen, in my lab will organize everything for you, and we'll share the QR codes right now that you can use and have on your phone to be able to then ask Colin Skeen, my colleague, to be able to get a kit and to be able to be informed as to what your microplastics are. I discuss that on the phone with you after the results are in, and then we try to help you manage that better. Thank you so much. I hope that you'll enjoy being part of the study. I hope you'll consider being part of the study, and thank you for your attention today. QR codes that you can use to be able to be part of the study. Thank you so much.